Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we are going to look at isometric operators. So in this topic, we will define what it means for a linear operator to be isometric. We will consider some consequences. We will also look at some useful examples. A linear operator A that maps a vector space to itself is said to be isometric if the 2 norm of A applied to U is equal to the 2 norm of U for all vectors U in that vector space. What this means is that A does not change the length of any vector. It may be pointing in another direction, but the length of that vector will not change. For example, the identity operator I is isometric, as is any permutation matrix. That is a matrix that has exactly 1, 1 per row, 1, 1 per column, and zeros everywhere else. All of those matrices are isometric operators. Now, the word isometric means same measure. So that sort of suggests what the property of such an operator is. Here's our first theorem. The null space of an isometric linear operator A is the zero vector. And thus, for finite dimensional vector spaces, A is one-to-one and onto and thus invertible. Proof. If U is an element of the null space of A and A is isometric, then note that the 2 norm of A applied to U must equal the 2 norm of U, and that must be 0 because A applied to U is the 0 vector. But the 2 norm of U is equal to 0 if and only if U is the 0 vector. Thus, A applied to U is equal to 0 if and only if U is equal to the 0 vector. That is, for A being an isometric operator. Thus, the null space of A is simply the 0 vector. Thus, if A is an isometric matrix, then A is invertible. Because after all, a matrix that is square is invertible if and only if it is one-to-one and onto. It is one-to-one and onto if the null space is just the 0 vector. Theorem. A linear operator on a finite dimensional vector space is isometric if and only if A times its adjoint equals its adjoint times A, and that is equal to the identity operator. Proof. Well, if the 2 norm of A applied to U is equal to the 2 norm of U, we can square both sides. Therefore, the inner product of A applied to U and itself is equal to the inner product of U and itself. Now, this is true if and only if this statement is true, for after all, we can move the linear operator A from the right-hand side of the inner product to the left-hand side by taking its adjoint. Also, the identity matrix is equal times a vector is equal to that vector. Now, this is true if and only if those two operators are equal. Thus, the adjoint of A times A must equal the identity map or operator. And for finite dimensional linear operators or square matrices, This guarantees that A times the adjoint of A is also equal to the identity operator, or in our cases, the identity matrix. Theorem: a finite dimensional isometric linear operator is normal. Proof: from the last theorem, we have that A, the adjoint of A times A is equal to the identity, which equals A times its adjoint. Therefore, A commutes with its adjoint, and so therefore, A being an isometric linear operator, it must be normal. Now, up until this point, we have emphasized that the most appropriate interpretation of a matrix is to see it as being a collection of vectors where each column is a vector. Thus, very often we have written an m by n matrix as a collection of n column vectors, each column vector being an m-dimensional vector. Now we're going to use a slightly different notation. To emphasize that these are the column vectors, we will use vertical ellipsis to indicate that the first index is supposed to include all possible first indices, meaning all the rows in the kth column. As you'll recall, the second index indicates which column we're in, the first index indicates the row. Okay, so it's a little bit clear that we are indicating a column here. Similarly, we will use a bold-faced A subscripted K, ellipsis to represent the kth row, and the horizontal ellipses are indicating that we are using all entries within that row. So, for example, here we see all n entries in the kth row that would be represented by the vector on the left. Consequently, we can have a matrix either represented by n rows or n columns, each of which is a vector that is m-dimensional, or we can represent the matrix as m row vectors, each of which is n-dimensional. Now, why are we doing this? Well, we are doing this so we can now define the transpose of either a row or a column, or the conjugate transpose if the matrix is complex. So, the first vector there is a column vector, but if we take the transpose of it, it becomes a row vector containing the m entries in the kth column. The second version down is simply what happens if we take the conjugate transpose, which are the same entries in that row vector, but each entry is conjugated. At the bottom, A sub k ellipses represents the kth row. So if we take the transpose of that row, we get a column vector that contains n entries. On the right at the bottom, we have the same except when we take the conjugate transpose. So it's the same entries, but each of the entries is conjugated. Thus, we have that a matrix can either be represented as n column vectors or m row vectors, as we see on the left. Consequently, the transpose can be seen as a matrix of n row vectors, each of which is the transpose of the column vectors of the original matrix, or we can see it as a collection of m column vectors, each column vector of which is the transpose of one of the m row vectors of the original matrix. The same goes for the complex conjugate transpose. However, in that case, we have to take the complex conjugate of each entry in those vectors. Theorem. For finite dimensional vector spaces, if A is an isometric matrix that maps a finite dimensional vector space to itself, then the columns of the matrix A form an orthonormal basis. Proof. Suppose that A is isometric and A is comprised of n column vectors, each of which is an n-dimensional vector. Well, in that case, the adjoint of A times A, well, the adjoint of A is represented by a matrix of n rows, each row of which is either the transpose or conjugate transpose of the corresponding column vectors of the matrix A. So now, if we try to calculate the product of these two matrices, notice that because we've taken the conjugate even for complex matrices, then consequently every single entry of the resulting matrix is the inner product of one of the columns of the matrix with another column of the matrix. However, you'll recall a few days ago we introduced a lecture where we had a different interpretation of the inner product, namely one where we take the transpose of the first vector or the conjugate transpose of the first vector if the vector is complex. Now, notice that of all these inner products, only the inner products of the column vector with itself is equal to 1, and all other inner products are 0. What that says is that the columns do indeed form an orthonormal basis. Thus, the columns of an isometric finite dimensional linear operator form an orthonormal basis. Similarly, for finite dimensional vector spaces, if A is isometric, the rows of the matrix form an orthonormal basis. So suppose now that A is isometric and is comprised of these n rows. Okay, now we will use the property that A times the adjoint of A is equal to the identity matrix. So here we have the matrix A, and each of the rows is the adjoint of each of the rows is taken, which creates n columns. If we now multiply out these two matrices, you will notice that we are not really getting the inner product, but rather you'll note that each of those is the conjugate of the inner product. Okay, well, fortunately in this case, it doesn't matter because the result is either 1 or 0. And if the conjugate is a real number, or if the inner product is a real number, then it doesn't matter. So indeed, here we see that, yes, once again, the inner product of each of the rows with itself is equal to 1, and the inner product of any row with any other row is equal to 0. Consequently, the rows also form an orthonormal basis. Here's another interesting theorem. The determinant of a real isometric matrix is plus or minus 1. What that means is an isometric matrix must preserve volumes. However, it may include a reflection that causes a switch in orientation. Proof. Well, A times the adjoint of A is equal to the identity, and the determinant of the identity is 1. However, the determinant of a product of operators is equal to the product of the determinants, and the determinant of the adjoint of a matrix is equal to the determinant of the matrix. If this is not entirely clear, remember that. How did we find the determinant? We applied a number of row operations to a matrix to get a matrix that is in upper triangular form. However, if we were to take the transpose of all of those operations, then that would end up with a number of transformations in the opposite order multiplied by a lower triangular matrix with the same entries on the diagonal. The determinant of each of the other row operation matrices would not change, and consequently the determinant would continue to be the product of the diagonal entries. Okay, so therefore the determinant of the adjoint of A is equal to the determinant of A, and thus the determinant of A squared is equal to 1, thus the determinant of A can be either plus or minus 1. Now, a few further definitions. If a real square matrix is isometric, they actually call it an orthogonal matrix. Also, if a complex square matrix is isometric, we call it a unitary matrix. In both cases, the rows and the columns form an orthonormal basis for R to the n and C to the n, respectively. Now, a few further definitions. If a real square matrix is isometric, they actually call it an orthogonal matrix. Also, if a complex square matrix is isometric, we call it a unitary matrix. In both cases, the rows and the columns form an orthonormal basis for R to the n and C to the n, respectively. So a few examples. In R2, the only possible isometric matrices are these rotation matrices. So on the left, we see that the determinant is cos squared plus sine squared, which is equal to 1. And we do note that the two column vectors are orthogonal, as are the two row vectors. All right. So that has determinant 1. If we swap the two rows, a row swap has a determinant of -1, and therefore the matrix on the right is also an isometric matrix or an orthogonal matrix, and its determinant is equal to -1. In 4 dimensions, on the left, we see an isometric or an orthonormal matrix in R4. You can take a look. Again, each of the vectors has 4 entries equal to 1/2. A half squared is a quarter. 4 times a half is 1. The square root of 1 is equal to 1, and thus each of those columns has a 2 norm of 1. Also, you'll notice that each of those vectors is orthogonal to the other 3 vectors. You'll note, therefore, that the column vectors form one orthonormal basis for R4, but the row vectors form a second and different orthonormal basis for R4. On the right-hand side, we see something similar, but this is actually a matrix used in the fast Fourier transform. So, rather than having a 1/2 multiplying every single entry of the matrix, I've factored out the 1/2. But assume that each entry in that matrix is multiplied by 1/2. If you were to calculate the inner product of any 2 columns in that matrix, you would find that their inner product is 0. Remember, you must take the conjugate of the first vector in the inner product for complex matrices or complex vectors. Also, you will notice that the columns and rows in this case do form the same orthonormal basis. Now, when we get to infinite dimensional vector spaces, it's not so clean. So consider the delay operator. So the delay operator applied to a discrete time signal simply shifts every reading one step into the future. Consequently, all the entries are still in that vector, and therefore the 2 norm of that vector cannot change. So this operator is isometric. However, if we apply the advance operator to the result of the delay operator, we get the original signal back. So the advanced operator applied to after the delay operator does give the identity operator. The problem, however, is if we apply those 2 operators in the opposite order, then we do not get the original signal back. We get the original signal back with a 0 in the first location. Consequently, even though the advanced operator multiplying the delayed operator equals the identity, the delayed operator composed with the advanced operator does not equal the identity operator. So things get a little bit dicey, but you just have to be careful. Not everything applies in infinite dimensions. Following this topic, you now understand what it means for a linear operator to be isometric. You understand that these are invertible in finite dimensional vector spaces. You also know that the rows and column vectors of isometric matrices form orthonormal bases for the corresponding vector spaces. And you are aware that for real matrices, such operators are called orthonormal matrices, and for complex matrices, they are called unitary matrices. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!